Hello, hello everyone. Uh, Today I am going to discuss about the application of Lagrangian formulation. If you need an entire derivation of Lagrangian formulation, you can tell me. I will upload it. Okay. So in the application of Lagrangian formulation, we have a two application. First one is a simple pendulum, and second one is Atwood machine. So in the simple pendulum, we are considering a simple pendulum from O to A. It oscillates from O to A of radius S, and theta be the angular displacement, and L is the length or effective length of the pendulum, and M is the mass of that metal ball. Okay. So as we know, so this is the arc. OA is the arc. So uh, that's value is yes. So if a theta is equals to arc by radius, so whatever we have an angle that we define by arc by radius. So we know that the value of arc, that is yes, a radius is L. So the equation, if we need a arc value, then S is equals to L into theta. Then we have a velocity of the pendulum. So velocity, it can be defined as rate of change of displacement. Okay. So S is our displacement. ds by dt is equals to, as we know, in the above equation we have found S is equals to L into t. Just substitute that. So L is a constant. So d theta by dt can be written as theta dot. This is a thing. So here what happened at point O. So here point O, the potential energy is zero. So here potential energy, the stored form of energy is going to be zero. At point A, potential energy is given by. So when a particle moves O to A, then here we have some kind of potential energy. As we know, potential energy formula is mgh. So here we are taking a potential energy as a U. U is equals to mgh. So here H is O to B. So O to B. This is the height. Okay. So just we are considering the uh, small height of this thing. So H is equals to OB. So if we want the OB, we have uh, uh, if we want this OB, we can subtract OC minus BC. If we subtract OC minus BC, we get this value. Okay. So that only I am written here. OC minus BC. MG is equals to OC value is L, and BC, this B to C. So this is if we consider from the Pythagoras theorem, this is a hypotenuse, this is the opposite angle, this is the adjacent one. So cos theta is defined as adjacent divided by hypotenuse, that is L into cos theta. Okay. Then U is equals to mgl. Here we took L as a common thing, that 1 minus cos theta is remaining. As we know that from the Lagrangian, L is equals to T minus V. So kinetic energy is equals to half mv square. Okay. So here V square already we have defined over here, that is L into theta dot. That only I am writing here, half m into S square into theta dot square. So V is equals to L into theta dot. So L, this is the Lagrangian equation. Again we are writing L is equals to T minus V. Okay, or T minus U or V. You can take anything. So this defines the potential energy. Okay, so just substitute over here. So we have the kinetic energy, that is half ml square theta dot square, minus already we found the potential energy, that mgl into 1 minus cos it. Just substitute here. So here what happened, we have to differentiate this because we know that the Lagrangian formula is mm, d by dt of dou L by dou theta dot. If we taking a generalized coordinate as a theta, then we are writing a theta. If we taking a generalized coordinate itself, then we are writing a q. uh, there is no restriction, we have to take only theta or we have to take only q. No, not like that. As wherever the case is, like when we are taking a polar coordinates, or when we are speaking about some radius vectors and all, there we position vector, there we can take r theta anything. Okay, x we can take anything, because q is a generalized coordinate that shows some other quantities also. D by dt of dou L by dou theta dot Okay, so minus dou L by dou theta is equal to 0. This is a Lagrangian equation. So to satisfy this, we have to to satisfy this, we have to find these two equations or these two derivatives. Okay, so partial derivative that we are found here. Dou L by dou theta, this term. Okay, so here what happened? MGL remains as it is. So minus cos theta, it is this differentiation becomes plus minus of sin theta. Okay, so minus into minus already plus happens. Cos theta differentiation is minus, so minus sin theta. Okay, dou L by dou theta dot is equals to so here what happened, half ml square into 2 theta dot. So these two get cancelled, ml square theta dot is remaining. Then L becomes, so here L what happened, so just substitute all the things in this equation. So here whatever d by dt of ml square into theta dot plus mgl sin theta is equals to 0. Okay, so if differentiate this, here ml square is a constant one, theta dot is a variable, so d theta dot about dt it can be written as, so this is like this. So this can be written as theta double dot. Okay. So mgl sin theta is equal to 0. Divide above equation by ml square. If we divide above equation by ml square, here what happened? This thing cancels out. So here ml is cancelled. So only divided by L is remaining, and along with the sin theta is equal to 0. This equation represents a simple pendulum equation. So here we are considering a first case, that is if I consider sin theta which is equal to the theta, let's consider sin theta approximately equal to theta, then what happens, theta double dot is plus g into theta divided by L equals to 0. This is first application of Lagrangian formulation. Okay, if you want to take a screenshot and all, you can take. So I hope you all got this entire derivation. Thank you for watching. Thank you so much. Bye bye.